Hi guys, welcome to our Silndi YouTube channel. Today we're building a distance measurement system using an ultrasonic sensor, and we'll display the distance indication using a set of LEDs. If you enjoy learning, building, and improving things by yourself, make sure to subscribe and hit the bell icon so you don't miss our upcoming videos. Let's get started. These are the components required for this project: 3 LEDs, 3 1 kilo-ohm current limiting resistors, an ultrasonic sensor module, a breadboard, jumper wires, and an Arduino Uno board to control the entire system. Let's assemble the circuit step by step. Okay, our hardware setup is ready. Now let's take a quick look at the overall code architecture. First, we define a set of constants for the pin assignments and the distance threshold values. This keeps the configuration clean and makes the code easier to modify later. Next, inside the setup function, we configure the required pins as input or output depending on their roles in the circuit. For better structure and readability, the distance measurement logic is implemented in a separate method. This method handles the ultrasonic trigger signal, measures the echo time, and converts that value into a distance. I will explain the distance calculation principle separately. Inside the main loop, the program continuously measures the distance and compares it with the predefined threshold values. Based on those conditions, the Arduino activates the corresponding LED to indicate whether the object is at a safe distance, a warning distance, or very close. But the real question is, how does this ultrasonic sensor actually measure distance? Let's take a moment to understand the principle behind it. When we trigger the ultrasonic sensor, it emits a short burst of ultrasonic sound consisting of about 8 cycles at 40 kHz. This means the sensor sends a small packet of sound waves into the air and then waits for the reflected echo to measure the distance. After transmission, the module automatically sets the echo pin high and waits for the reflected wave. Once the reflected ultrasonic pulse is detected, the echo pin goes low. The Arduino uses the pulse-in function to measure the width of this high signal on the echo pin. This duration represents the total round-trip time of the ultrasonic wave from the transmitter to the target and back to the receiver. Now let's examine the calculation. The speed of sound in air at 20 Celsius is approximately 343 meters per second, which we approximate as 340 meters per second for simplicity. Converting that into centimeters per microsecond, 340 meters per second equals 34,000 centimeters per second. Since 1 second equals 1 million microseconds, the speed becomes 0.034 centimeters per microsecond. Using the fundamental wave equation, distance equals velocity multiplied by time. We multiply the measured duration by 0.034 to get the total distance traveled by the wave. However, this is the round-trip distance. Since we only need the one-way distance to the object, we divide the result by 2. So the final formula becomes distance equals duration multiplied by 0.034 divides by 2. The function also includes a timeout of 30,000 microseconds. If no echo is detected within this time, pulse-in returns 0, and the function returns -1 to indicate an out-of-range condition. Keep in mind that environmental factors such as temperature, humidity, and air pressure can slightly affect the speed of sound, which introduces minor measurement errors. And that is the complete technical principle behind ultrasonic distance measurement using time-of-flight calculation. Once the code is uploaded, this is the system in action. As you can see, the LEDs indicate the distance between the sensor and the obstacle in front of it. Feel free to experiment with the code, modify the distance thresholds, or add more indicators. DIY projects are the best way to learn electronics and programming. That's it for today's project. If you enjoyed this video, don't forget to like and subscribe. See you in the next project.